Hello, wonderful people. Here we are, the beginning of a new chapter, 14, Satellite Motion. And what's the big idea of satellite motion? Well, the path of an Earth satellite follows the curvature of the Earth. So, some of this should be familiar vocabulary. Let's get into it. Where's my arrow button? There we go. So, a stone thrown fast enough to go a horizontal distance of 8 kilometers during the time, 1 second, it takes to fall 5 meters will orbit the Earth. So if you throw it fast enough so that it goes sideways 8,000 meters, during that time it will fall 5 meters. But the trick is if you go 8 kilometers, the Earth is curved 5 meters down. So there's the picture of dropping the ball. Then you throw the ball a little harder. And where's that picture? There's the picture. She throws the ball all the way around the planet and it comes back and hits her in the back of the head. Now, here she's standing on an asteroid. You can be on an asteroid and throw a ball so that it will come back around and hit you on the back of the head. Oh, I don't have the numbers off the top of my head, but I'll have to go look it up. There are asteroids that are just 1 mile or a few miles across. Like an asteroid that's 1 mile across, you could run fast enough to go into an orbit. And an asteroid that's like 10 miles across, you can throw a ball to go into an orbit. Now, where's that picture? So here's the picture. 5 meters, that's how far it will fall in 1 second. So if you throw it fast and faster and faster, well, here you see how it hasn't hit the ground because the ground is starting to curve away. That's the idea. If you go 8,000 meters out, the Earth will have dropped down 5 meters. Now, how do I know this is true? Well, I've seen it. Yes, you can see this. Where can you be standing on the Earth where you can see 8,000 meters, which is about almost 4 miles, and the Earth is perfectly flat? Well, reasonably flat, on the ocean. So when I was in the Navy, when we're out in the middle of the Atlantic, you could be at the level of the sea, of the ocean, just climb down the ladder. It's an aircraft carrier, and you would be level with the tops of the waves. And if you just looked out, you could see a ship that was 10 meters tall. You would only see the top half of that ship. And that's 4 miles away. You could see ships that were 30 miles away. But they had to be really tall because you would not see the bottom for 8 times 5, the bottom 40 meters of a ship. So I just did the math in my head, and that makes sense. So if it's about 32 miles away, it would have to be a big ship, like a container ship or what are those oil carriers? An oil tanker. Those were more than 40 meters tall. So you couldn't see the bottom half of that ship, but you could see the top half of the ship. So, we're what, 3 hours away from Boston? Even if you go to the ocean, you can stand on the beach, and if you can find a ship that's a few miles out, get some binoculars, and you can see that you don't see the bottom half of the ship. Even if it's just a speedboat 2 miles away, you can't see the bottom half of that speedboat. So that's one way I know it. I've seen it. Another way is I know the math. I can do the math, and all this stuff makes sense. And that's what I'm trying to teach you how to do. So here we go. Let's do some reading. The 5 meter drop for each 8,000 meter tangent, that line is tangent to the curve of the Earth, means that if you were floating in a calm ocean, you'd be able to see only the top of a 5 meter mast on a boat 8 kilometers away. So if the mast was 5 meters tall, which is a kind of normal sized sailboat, a little on the small side, you would only see the top of the sail. Where's that picture? I'm trying to get to one. Here it is. So here's the way it works. It goes 8 kilometers and it falls 5 meters. And it hasn't hit the Earth yet, so it's still moving 8 kilometers a second. And then it falls 5 meters down, but it hasn't hit the Earth yet. It goes 8 kilometers out and falls 5 meters. So this is exactly how, if there's no air, you can throw a ball. Whoops, hit the wrong button. There we go. If you throw a ball so that it's going sideways at 8 kilometers a second, it will never hit the Earth. Right? Do you get that? Because there's 8 kilometers, 5 meters, it doesn't hit the Earth. So if you throw the ball so it goes this far and falls 5 meters, it hits. But if you throw it so it goes 8 kilometers out, it's not going to hit the Earth. Okay, so now let's go back. I was showing you the pictures. Now I'm going to read the text. Section 14.1, Earth satellites. How fast would the stone have to be thrown horizontally for it to orbit the Earth? The stone dropped from rest accelerates at 10 meters per second squared and falls a vertical distance of 5 meters during the first second. So the orbital speed for close orbit about Earth is 8 kilometers per second. That is 29,000 kilometers per hour. And if you move that over into miles per hour, it is 18,000 miles per hour. 18,000 miles per hour. So a jet that's flying way up high at a really fast speed is going 500 miles an hour. That's a fast jet. That's the big airliners. 500 miles an hour is still like it would have to go 40 times faster almost. It's not even close to being able to orbit the Earth. At that speed of 18,000 miles per hour, atmospheric friction with the air, would burn an object to a crisp. So even if you could get that jet to go from 500 up to 18,000 miles an hour, if it was going at 18,000 miles an hour for 10 seconds, that whole thing would burn completely away. All the metal would melt, all the people inside would die, there would be nothing left. It would all vaporize. That's how incredibly hot it gets. So, air friction, you just can't be at this speed and be anywhere near air friction. So that means that a satellite must stay 150 kilometers or more above the Earth's surface to keep from burning due to the friction. And normally it's more like 200 at a minimum. So how fast does a stone have to be thrown to orbit Earth? 18,000 miles an hour. 14.2, circular orbits. A satellite in circular orbit around Earth is always moving perpendicular to gravity and parallel to Earth's surface at a constant speed. So, in a circular orbit, the speed of a satellite is not changed by gravity. In a perfectly circular orbit, the speed is constant all the way around. Compare a satellite in circular orbit to a bowling ball rolling along a bowling alley. Gravity acting on the bowling ball does not change its speed. Gravity pulls downward, perpendicular to the ball's motion, and the ball has no component of gravitational force along the direction of the alley. So if the ball is being pulled straight down, but it's moving sideways, then the ball has no component of gravitational force along the direction of the alley. So gravity isn't going to move it. And there's the picture. Gravity force is pulling it straight down, but as it's moving down the alley, it's going perpendicular to this, 90 degrees away. So the speed of the bowling ball and the satellite are not affected by the force of gravity because there is no horizontal component of gravitational force, no horizontal component, something going side to side there. So the satellite is always moving at a right angle, perpendicular, to the force of gravity. it doesn't move in the direction of gravity, which would increase its speed. So if this did move down some, well, gravity would be pulling it down, so its speed would increase. But its speed never changes. Its speed is perfectly constant. Its velocity changes, right? Because velocity is direction. So it's always changing direction around here, but the speed is exactly the same because it's in a circular orbit. So no change in speed occurs, only a change in direction. There we go. So for a satellite close to Earth, not at the surface, but close to Earth, above the air, the time for a complete orbit around the Earth is about 90 minutes, and we call that its period. So every 90 minutes, if you look up, you can see the International Space Station go by. And for higher altitudes, the orbital speed is less and the period is longer. So if you go to a much higher altitude, it can be 100 minutes or 2 hours or even 24 hours. And that's one of the tricks. So communication satellites are located in orbit 6.5 Earth radius, radii plural, from Earth center. So their period is 24 hours. So if a satellite is orbiting the Earth, going around the Earth once every 24 hours, and the Earth is rotating once every 24 hours, if you're standing right there on the Earth and you look straight up, you see the satellite. And as you go around the Earth, as you go around, so does the satellite. So if you're standing, it has to be on the equator. If you're standing on the equator and you look straight up, you can see that satellite standing still in the sky. It never moves. It looks just like a star. This period, and this is so I'm going to reread it. Communication satellites are located in orbit 6.5 Earth radii from Earth center, so that their period is 24 hours. The period is 24 hours. This period matches Earth's daily rotation, so they orbit in the plane of Earth's equator, and they are always above the same place. Now, the moon is further away, so it only orbits the Earth once every 27 days. 27.3. So if you're standing here and you go around the Earth one day, the moon has only moved about that far. And then you go around again and it will be there. And after 27 days, it will be back to the same spot. So the International Space Station, ISS, there's a picture of it. And this is a pretty recent picture because it has a lot of the structure in there. It's 360 kilometers above the Earth, so it's way above the atmosphere. We talked about all that already. So, describe the motion of a satellite in relation to Earth's surface and gravity. That's what we just did in circular orbits. If you wanted to pause now and go answer the questions for section 14.1 and 14.2, that would make sense. In fact, you know what? I'm going to stop the video there. So we'll do 14.1 and 14.2 together, and we'll do 14.3 in a separate section. Okay, bye-bye.